guys, this is the second tutorial related to k nearest neighbors. However, in this tutorial, we will learn how to build KNN models for regression purposes. So let's get to it. Okay, so first we're gonna start by loading the data or importing the data into the notebook using pandas. So we start with import pandas as PD. And then I like to always use the df label for data frames. So PD read CSV. And in this case, the name of the data file that we're going to use is called calories, if I remember correctly. All right, so this is the data. Let's clean it up a little bit first. So user ID, so that's just an ID that doesn't provide any information, so we can ignore that. So all right, so this is the data, and let me give you a quick background on this data set. So it is a regression data set because the purpose is to use these features to predict calories. Okay, and just as a background, so this is data that comes, I think, from a very small study in which they were trying to identify what factors may or may not affect the number of calories that adults will burn during a workout session. Okay, so we have gender, age, height, weight, the duration of the workout session, heart rate, and body temperature. And again, the goal is to use this information to predict the number of calories. In this tutorial, we're going to be using k nearest neighbors as the model to predict calories. Okay. All right. So let's get to it. So when it comes to building models, again, especially from the machine learning standpoint, it's very common to use X as the label for the input data and Y as the label for the target feature. So let's do that. So we're gonna drop all the columns. No, we're gonna drop the calories column, and that's gonna be our input, and Y is gonna be our target. So let's see, I missed the argument 1 there. Oh, and I also miss a parenthesis. So what do we see here is that now under X we have gender, age, height, weight, duration, heart rate, and body temperature. So we're gonna use all of that information to predict calories. All right, so one thing that I want to emphasize here, especially when you're building k nearest neighbors, is that all of the features that they need to be numeric. Okay, why numeric? Again, because remember that the k nearest neighbors relies on the Euclidean distance, so then we need numbers to compute the Euclidean distance, basically. Okay, and in this case, because gender only has 2 labels, either male or female, we can easily map that into zeros and ones. One way to do that is just by doing something as follows. So gender equals to gender. Let me do this. Gender, and then we can use the command map to do the mapping. So female is gonna be 0 and male is gonna be 1. Now if I rerun this and then X, now we see that under gender, now we only see zeros and ones. Okay. All right, so we have the input denoted by X, we have the target denoted by Y. Now we are ready to run a 5-fold cross validation. So there is a typo here, cross validation with k equals to 10. So we're gonna be building a k nearest neighbors with 10 neighbors. And as I explained on the previous tutorial, so the idea here is for a new observation, identify the 10 closest points in the case of 10 neighbors, and in this case, looking at the calorie values for those 10 neighbors, take the average and that will be the predicted calories for that new observation. Okay, why do we need, or why do we care about fivefold cross validation? Cross validation is a framework that allows practitioners to evaluate models. Why do you want to evaluate your model? Is because you want to see how good your model is at predicting the target variable. Okay, keep in mind that the main purpose of predictive modeling is just to build good models that generate good predictions. And how you can quantify that is by performing what is called a cross validation strategy. Okay, all right, so then let's get to this. So first, let's start loading all the different functions that we need to run this cross-validation strategy. So first, we start with sklearn, model selection, import. We can use cross-valid score. Then we're gonna be importing k-neighbors regressor. And also we need the cross-validation strategy. So it's gonna be, in this case, in the case of regression, we're gonna be using k-fold. Okay, I think that's pretty much what we need by now. So then here we define the cross-validation strategy. So we are using 5 folds. We're shuffling the data before we split it. And then here we just random state, we're setting the seed. Here we define the model is a k-neighbors using 10 neighbors. And then here we define the cross-validation experiment. So first you need to enter the model, then the input, then the target, then the cross-validation strategy, and then how you're going to evaluate the model. In this case, we're using the root mean square error as a metric to quantify model performance. N jobs equals to -1 is just an instruction to Python to use all the available cores that you have in your computer. And then here we just print the average root mean square error and the corresponding standard deviation of those 5 values. So let's run this. All right, so then this is the average root mean square error, 7.05. Okay, and if you're wondering what are those individual root mean square errors, so then you just type k and then cv, and it will show you 5 values. And the reason why it show you 5 values is because this is the root mean square error that you obtain by leaving the first fold, treating the first fold as your test data set. This is the root mean square error that you obtain by treating the second fold as your test data set, and so on. And by taking the average of these, that's the number that you get here, 7.05. Okay. And typically, when you are just running or building these models and running your cross-validation strategies just with raw data, so basically here is you are just starting somewhere, right? You need the benchmark, and then after that, what you're trying to do is just to improve the results. Now, something that I want to emphasize here is that notice that the data, right? Let's print again X here. The data is on different scale, right? So gender is a 0, 1, age is, and we can quickly report the summary statistics. So gender is 0 and 1, age goes from 20 to 79, height goes from 123 to 222, and so on. So then the features are on different scales. And as I emphasized on the first KNN tutorial, so having the features on more or less the same scale is very crucial, especially on models or techniques in general that rely on the Euclidean distance. So let's rerun this, but then now taking care of that. Okay, so I'm just gonna copy the same code, and then here I'm gonna have from scalar pre-processing, and then let's use the standard scalar. I like to use the standard scalar a lot. So, and then what we're going to do here is we're going to add one more step. We're going to use the pipeline command to create a pipeline. So make pipeline, then standard scalar, and then k neighbors. Again, as yeah, so this is another of those important commands if you're using scikit-learn and if you're building machine learning models. That's another important command that you need to know. Okay, so make pipeline basically just create a sequence of steps. Okay, so first you standardize the inputs and then you build the model basically. Okay, now let's rerun this, but then you just by including that to see if we get better results. All right, so then now the new 5-fold cross-validation root mean square error is 4.94. Notice that we went from 7.05 to 4.94. And when it comes to the root mean square error, smaller values are preferred because the smaller the root mean square error is, that means that the closer the model predictions are to the actual true values. Okay, so it's a significant improvement. Okay, so and again, that highlights how important it is to have all of the input data more or less on the same scale when it comes to k-nearest neighbors, because it relies on the Euclidean distance. Okay, so this is our new benchmark, 4.94. Okay, then a typical next step when it comes to, okay, how am I going to improve this model? Okay, so there are a few different ideas that you will consider, right? So depending on how long you've been in the machine learning field, right? You will think about feature engineering. You will think about hyperparameter tuning. Okay, so in this case, what we're going to do is, let's say if we can improve the auto sample performance by running a very simple experiment, a very simple Optuna experiment. Okay, so if you're not familiar with Optuna, so Optuna is a very popular hyperparameter Python library. Okay, so then the goal of Optuna is just to run experiments so that you can find the configuration, the model configuration that generates the best auto sample performance. Okay, it's very flexible, it's very easy to use. Okay, all right, so let's get to it. So in this case, again, when it comes to k-nearest neighbors, so the reality is that we don't know whether 10 is the right number of neighbors. Okay, that's something that we need to explore. Okay, so what we're going to do is we're going to run experiments in which we're going to be changing the number of neighbors. Okay, so we're going to start with 2, then 3, then 4, and so on. Okay, so let's do that. So we're going to, let me copy most of these commands here. What we're going to do is we're going to import Optuna, and then after that we're going to start defining the experiment. Okay, so here we define the range of values that we want to consider for k, and k is a number of neighbors. So I usually start with 2, and let's go all the way to 30. And then here we're defining the model, right? So then on the model, we're defining it with pipeline. So first it's going to standardize the data, then it's going to build the model. Notice that k, this k is defining here. Okay, and then here, that's where we define the cross-validation strategy, and then here we actually run the experiment, and then we extract the average root mean square error. Okay, now the first thing when it comes to hyperparameter tuning in KNN is the number of neighbors. However, there is another important hyperparameter that has to do with weights. And let me quickly explain you what weight is, okay? So typically weight is just once um, once the algorithm identify the k closest points, right? So if you don't specify anything else, right, it will take the average. In the case of regression, it will take the average of the target values associated to those k points. However, someone may argue, okay, but I want to put more weight on the points that they are closer to the new observation. Okay, so if that is the case, so this command weight will allow you to do that. So there are two options for weight. So you have uniform. So that means that once you identify the k neighbors, just take the average of those. And distance, basically, it will compute the average, but it's not going to be just your regular average. It's going to be a weighted average. So then the closer the point or the closer the neighbor is to the new observation, the higher the weight it gets. And the weights are going to be computed based on the distance. It's going to be the inverse of the distance. So then the smaller the distance is, the higher the weight that observation received. That's basically it. Okay. So we're going to play with that just to see if we can get better results. Okay, so then now we have this as part of the arguments here. All right, so then that's basically our how we will define our Optuna experiment. So then we need to define it as a function, trial, and then this is what's gonna generate combinations of k and weights. And remember that k represents the number of neighbors, and weights now is going to be the weights, whether we consider uniform or distance. Okay, so that's basically what we need to define for our Optuna experiment, and now we're ready to run this. Okay, in this case, we're going to create a study because we are doing regression, and then we are considering the root mean square error as a measure of performance. So then we want to minimize that, right? The smaller the root mean square error is, the better. So then the direction that we want to go is to minimize. Okay, just for illustration purposes, let's run only 50 trials. So then basically, again, here we're defining the study, and then here we are running this process basically 50 times. And what is going to change is here, right? Is the combinations are going to change. Okay, so if I run this, so you can see the trial one, and it gives you the corresponding value from trial one and what was the hyperparameter combination. Okay, so this is a fairly small data set, so it runs pretty quickly. And now we can extract here, if I do just study best params. So yeah, the best hyperparameter combination based on those 50 trials is 11 neighbors and using the distance as the weight. Okay, and let's see what was the value or the arrow sample root mean square error. So then study best value. So 4.76. Notice that our benchmark was 4.94. So then we were able to even get better results just by running a very simple Optuna experiment. And then now we are on 4.76. Okay, and then, you know, a future potential next step, it will be, okay, maybe let's start looking into feature engineering, right? So maybe start creating interactions among these features, or yeah, interactions. Yeah, that will be my next steps if I, you know, if I want to keep improving this result. But then, yeah, for illustration purposes, again, just by running this simple Optuna experiment, we went from 4.94 to 4.76, which is an improvement. Okay. So yeah, so again, when it comes to KNN, as I mentioned in the first KNN tutorial, it's a very simple algorithm, very easy to understand. It is flexible in the sense that you can use it for classification purposes and regression purposes, like in this case. Remember to make sure that the input data, more or less, it has to be on the same scale, and you see the effect, right? This is without doing any transformation on the input. This is standardizing the input, and you know, as a potential next step, you can also consider tuning the model a little bit. Okay. All right, that's all I have for this tutorial. See you on the next one.